Let's keep an eye first on the mating population proportions. Remember, only the normal homozygous or the heterozygous individuals can mate, and they appear in the mating subpopulation in proportions U over 1 minus W and 2V over 1 minus W. When we proceed to the issue of random selection, the idea is as follows. Select a male from the mating population, select a female from the mating population, and now we've got a pair of parents. We shall be very creative here and simply bow to stereotype and represent the genotype of the male in a blue color and the genotype of the female with a pink color. Since both males and females are restricted to either normal homozygous or heterozygous characteristics, there are 4 possibilities for the pairs of the genotypes. Both are normal and homozygous. The male is normal homozygous, the female is heterozygous. The male is heterozygous, the female is normal and homozygous, and both male and female are heterozygous. In the process of mating, each individual proffers one gene from their genotypical makeup. And the 2 genes, one from the male, one from the female, will then form the progeny's genotype. This is the genotype in the filial generation, the child's generation. Of course, all possible mixings are feasible under this setting. And so the child could have the normal homozygous Kappa genotype. The child could have the heterozygous genotype. The child could sadly be sick and have the lethal genotype. The probabilities of these happening, let's use the same notation we used earlier, but with a prime to tell ourselves that this is the filial generation. Let U prime be the probability that the child is normal and homozygous, 2V prime the probability that the child is heterozygous, and W prime the probability that the child is infected. Now, I haven't told you very much about the probability space at this point. Right? We're talking lightly about probabilities, but of course, underlying all of this, there must be a chance experiment. And here's where independence plays a central role. And independence here plays a role in 2 places. First, in parental selection, and second, in the selection of the genes from the individual parental genotypes. Let's take this in turn. So, the first experiment involves 2 trials. One selecting a male from the mating population, one selecting a female from the mating population. The idea of random selection implies that these individuals are selected independently and at random according to the probabilities on the upper right of your screen. So let's consider the 4 cases. In the case where both male and female are normal and homozygous, each of them has got a chance U over 1 minus W of occurring. Since males and females are selected independently under random selection, the probability of this is U over 1 minus W times U over 1 minus W. I've color-coded this to make it clear where these probabilities are coming from, one from the male, one from the female. What if the male is normal and homozygous and the female is a carrier? She is heterozygous. Well, in this case, the male has got probability U over 1 minus W. The female has got probability 2V over 1 minus W. And again, independent selection means we multiply the probabilities. Likewise, if the male is a carrier and the female is normal and homozygous. And finally, when both individuals are heterozygous, both of them are carriers. We have now got a stage where we got these a priori probabilities, which set the stage, set the table as it were. These probabilities represent the parental mixing possibilities under the assumptions that we have so far. To get to the filial genotype, we now have to select genes, one from each member. Okay. Let's take this in turns. To get a normal homozygous child, a child with two uppercase A's in their genotype, well, this can be done with any of the four combinations. In all four combinations, both parents have at least one uppercase dominant normal gene in their makeup. And therefore, all four cases can result in normal homozygous child genotype. What are the chances we want to allocate here? Naturally enough, we're not thinking about a conditioning setting. We're thinking about the conditional probability of a filial genotype emerging given a particular parental genotype makeup. So let's start with the normal homozygous child genotype. There are four possibilities, and the arrows going from left to right will tell you what is feasible. What is the probability that starting with two normal homozygous parents, you get a normal homozygous child? Well, each parent offers a dominant uppercase A gene with probability 1. They do not have lowercase a genes, and therefore that probability is 1 times 1. We assume that selection of these individual genes constitutes independent trials. What about if the male parent is normal homozygous, the female parent is a carrier, is heterozygous? Then the male parent proffers an uppercase A gene with probability 1. The female parent proffers the uppercase A gene 1/2 of the time, and therefore the probability is 1 times 1/2. Similarly, if the male is a carrier and the female is normal and homozygous, the probability is 1/2 times 1. And finally, if both of them are heterozygous, then each of them has got a 1/2 chance of proffering the uppercase A gene, and therefore you have a 1/2 times 1/2 probability in that case. Notice how the conditional probabilities fall into our laps, as it were, just by reading out from left to right what the circumstance is. What about the child genotype, which is a carrier, which is a mixture of an uppercase A and a lowercase a? Well, in this case, if the parents are both normal and homozygous, it is impossible for them to create progeny whose genotype is anything other than normal and homozygous. So there's a missing arrow from the first case. But the three remaining possibilities can all create carrier individuals. And the probabilities now are 1 times 1/2, 1/2 times 1, and the third is only one where a little thought is required. The third instance, we have two heterozygous parents, each with a mixture of genes. To obtain a heterozygous child, one of them will have to offer an uppercase A gene, the other will have to offer a lowercase a gene. Now, this can be done by the father offering the dominant gene, the mother offering the lethal gene, or vice versa, each of which has got probability 1/2 times 1/2. The picture on the screen might make things a little clearer. In the situation of a carrier, the male has got both genes, the female has got both genes, and there are four possibilities for the mixing. In one case, you find that both parents offer the clean gene. In one case, on the left end of your screen, both parents offer the lethal gene. And there are two possibilities in the middle, depending on who offers the lethal gene and who offers the dominant gene. All right, and now this leaves one last case, the case where the child has a disease. But this is only possible when both parents are heterozygous and each of them proffers the lethal gene, and this has got probability 1/2 times 1/2. We should pause and take a look at what we've constructed here. What is the sample space of this underlying chance experiment? Well, this sample space has got multiple elements. There's first the selection of the male genotype in the parent, then the selection of the female genotype in the parent, then the selection of the gene proffered by the male genotype, and then the selection of the gene proffered by the female genotype. We could abstract all of this out by saying the following. There are two tosses of a bent coin, whose success probabilities are on the upper right of your screen. These will tell you what the selection of the parental genotypes is. And then there are two more tosses, this time of a fair coin, which selects a gene at random from one of the two genes on each of the genotypes. So, two bent coin tosses and two fair coin tosses would describe the experiment. Of course, this is a rather complicated way to look at it. Right? We can simplify matters a little bit now, because we are now looking really just at settings where we have genotypes for parents and genotypes for children. And we can put all of this together and abstract all this information out very, very simply. As far as the genotypes of the filial generation are concerned, we could reduce this probability space to three elements: the two parental genotypes and the child's genotypes. In other words, a triple of genotypes completely describes for our purposes what this experiment is about. In this space, where the sample points are triples of genotypes, events are subsets of the space, and we have used informal language and notation to capture these events. Say, for example, on the left of your screen, you have the four possible parental genotype combinations. Each of these represents an event in the space of triples. For example, the two uppercase A, where both parents are normal homozygous, represents an event where the first two elements are normal homozygous, and the third, the child's genotype, is something. Of course, only one thing is possible in this case. But if both parents were heterozygous, then the child's genotype could be anything. These constitute the event descriptions. And the problem structure allows us to directly intuit modulo an assumption of random selection and mating, modulo an assumption of independence on multiple fronts, that the probabilities of the events on the left are given in the table, as you say, by simply multiplying out the elements together. The rest of the story in creating the probability measure is given to us via the conditional probabilities, which take us from parental genotypes to the filial genotypes. And these can be assembled, if one wishes, in another table like this. The rows of the table tell you what the parental genotypes are, the columns tell you what the filial genotypes are, and the conditional probabilities are filled in inside. Together, these two tables, or equivalently, the picture will tell you the entirety of the probability space. If we think of the probability space here as being described by triples of genotypes, we can extract the underlying probability measure at need by simply multiplying out the a priori probabilities and these conditional probabilities, which in the context of this flow of time, we'll naturally identify as transition probabilities. By simply multiplying them out term-wise, we get the probability of every atomic triple. All the atomic probabilities are now within our purview. Of course, this requires much more effort than we really need to put in. The conditional probabilities tell us everything we need about this particular experiment. We are now equipped to come down and ask and answer the question we started with, which is, what can one say about the distribution of genotypes in the filial generation? What is U prime? What is twice V prime? What is W prime? Of course, we would like an answer based upon the original proportions in the parental population. We turn to this next.